So we have to work on the acoustics. You see these little cutouts that we have here. So those create an echo. Morning. I know it's really early morning by Hyderabad standards. 10 is like considered like, most people if you ask in Hyderabad, they would have you believe that it's still dark outside at 10. So thank you for coming really early in the morning, right, for joining me on this course. And I know the focus of the course is on precast, so and 3D printing really doesn't belong under the category of precast, but I'll hopefully present a few things that will justify my presence here, right? So, what is 3D printing and why is there such a big buzz about it? Well, if you look at conventional concrete construction, what makes it clunky, what makes it slow is the whole process of construction. You have to assemble formwork, tie the formwork together, put your steel in there, then pour concrete, then eventually you de-shutter. So the whole process is very slow. So that is the first knock on precast regular construction with concrete. The other thing is that with concrete construction, we are often always stuck with rectilinear forms. A simple thing that one could ask is, why does a beam have to be rectangular? Right? Why is it that almost always we see concrete beams to be rectangular? Well, your answer would be, that's the way I was taught. You open any textbook, they will start off with a rectangular beam. But the question is, who told them to make it rectangular? And the steel people have already learned their lesson, because steel is a much more expensive material. And of course, steel doesn't have the advantage of casting on the field. But what is considered to be an advantage of concrete is turning into its Achilles heel. And what I mean by that is, because we went for expediency, we say, well, it's easy to construct. I can do it on site. So let me do something that's easy to do on site, and that is a rectangular formwork, right? So that's the reason why we make all our shapes to be rectangular, because the formwork is easy to write, right? It's ease of construction. What is the price that we pay? We basically end up making our structures very, very heavy, because if you look at a rectangular cross section, almost 50% of the material is really not doing anything. It's not contributing to the structural resistance. It is not contributing much to the stiffness either. What it is doing is adding to the weight of the structure. Now, there is this thing called the downward spiral. Now, what is a downward spiral? Those of you who've done reinforced concrete design would know that by the time the span of the beam increases beyond 7 meters or 8 meters, it's like a dog chasing its own tail. How do we go around doing with a rectangular beam design? Suppose I ask you to do a rectangular beam design with a certain loading. Say I increase the span to 8 meters or 10 meters. At some point, you'll realize that in order to meet the sectional demand or the capacity, sectional capacity demand, you would have to make the cross section bigger. Now, when you make the cross section bigger, it only brings in more weight. Right? So basically it contributes more to the demand. So at some point, at some spans around 10 to 12 meters, you'll realize that it's almost impossible to design a single RC beam, because the minute you start making the beam deeper or bigger, you add more weight, and to provide to that additional demand, you actually have to make the beam deeper. So basically that is the downward spiral we are talking about in RC design. And oftentimes we find that depending on the loading and the end conditions, the boundary conditions, the break-even point would be about 10 to 12 meters, beyond which doing a single RC just doesn't make any sense. You just cannot. So what do? Then we resort to pre-stressing. That is the next alternative, and that's where pre-stressing came about, from this whole downward spiral. Now, what is contributing to the downward spiral is all the excess weight that this structure is dragging when you try to meet the demand, because it is rectangular. Now, suppose I was able to take away material where it is not needed, go with even a simple I section, you'll realize that the same break-even point would happen much later. Because now I'm not adding extra weight unnecessarily. Right? And that is what is the biggest problem with the rectilinear forms, and we are stuck with rectilinear forms because we say, well, it's easy to do on site, right? So, but what if we could come up with a method of construction which allows us freedom from this formwork, whereas I can print whatever form I want. Right? The ideal dream would be to do it in situ. The ideal dream would be to provide this form live so that I'm able to print it and move away from the rectilinear shapes. move into something that is perhaps more form optimized or structure optimized, take away material where it doesn't belong, and give you a design that is actually structurally efficient. And so that is where we believe that concrete printing will have a niche impact. Can I just get these lights, I think? Just the front ones, huh? Okay. Yeah. So now, with that in mind, we start our journey in 3D printing. This is a pretty cool video of what you can do with printing. And so the whole point is that you're actually fabricating. So you're bringing in the materials of the process of fabrication, and it's a subset of what we call additive manufacturing. So you basically produce a structure additively. Typically, when you get into manufacturing, it is subtractive. So you start with a block of aluminum, you take away whatever is not needed, you end up with the form. So that is subtractive. Here it is additive because I'm being constructive. And how much can you go with it? Well, this is what you can potentially do. The material here is of course clay, but it can be done supposedly even with concrete. So I'm moving away. And if you look at this, if this were concrete, I don't need formwork. This would be done in real time, and I can give you these shapes which are not rectilinear. I can create all these surface features and all these things made out of concrete. Now, printing itself is not new. In fact, my colleagues in bioengineering have been doing it today. A lot of our human tissues, organs, we have not come to the stage of organs yet, but tissues certainly we're printing. Skin is being printed, scaffolds, bioscaffolds are being printed. All of these are being printed. So the technology is quite mature. In fact, if you look at it, it's almost 20 years old. Mechanical engineers do a lot of printing with plastics and metals. The difference of what we are talking about is this. What they typically do is millimeters to centimeters. They have other challenges, of course, when you go small, but our challenge is take it from this scale to something that is meters to tens of meters. So basically the rules of physics that would apply on the smaller scale are different. The rules of physics that apply on the larger scale are very, very different. So that's what we need to work with it, but the process remains essentially the same, and we are borrowing heavily from what they've already developed. We are not doing anything new as far as that goes. So how does the process of 3D printing, or what we call extrusion-based 3D printing, how does that work? Well, if you look at extrusion-based 3D printing, what we do is we take a structure, we will basically digitize it and store this in the form of layers. So basically, this structure exists in a computer memory in the form of layers. Right? Then the question is, how do I assemble these layers? So those layers, one after another, would be deposited in time, and what you essentially would end up with is a structure that is made up of all these multiple layers. And so that is the whole process. And this process has to be understood carefully, because whatever we get as properties or whatever we get as a response of the material, that depends on the way the material layers are stacked up and the way the material layers behave together. And please remember that this is done with no special attention that is given to making sure that the layers are bonded together, or we are not doing anything special to make sure the two layers stick together. It's just something that is fresh concrete that comes out. You deposit it as in the form of a layer. The layer has to keep its shape and definition, and another layer comes and sits on top of it in a matter of seconds. It's not even like you're allowing the concrete to set. So this whole process, basically, suppose building up this entire wall would take us about 1 hour or so, and we could raise that wall slowly, one layer at a time. Right? And again, the whole issue of resolution versus what we can do in terms of scale, that is what becomes important. So if I keep my layers to be very thin, to assemble something that is very high would basically take a long time, because every time the print head has to go around, do a loop, come back, and then it raises and then prints another layer. So if now I have, let's say, 100 layers as opposed to 50 layers, it's going to take more time, because the print head has to move around 100 times as opposed to 50 times. What do I gain there? When I start keeping my layers thin, I can actually give you much better resolution. So I can actually give you features on the wall. I can give you all kinds of variations in the texture and all these things in the wall, and replicate the surface features in much, much better detail. Or even the geometric features, I can replicate them in much better detail.
Most of the modular houses today are 3D printed.
No, we are not there yet. So, and I do want to stress on that point. I'll tell you why we are not at that point yet. Now, this is just to give you some examples of 3D concrete printing. This is what was printed for the World Fair in Dubai, the first so-called 3D printed structure. They wanted to showcase, done by a company called Icon, which basically printed this structure right that you see here, and this is the interior, and you see the Sheikh of Dubai. Unfortunately, they had to endure COVID, and it didn't see that big a launch as they would have liked to see. This is the first so-called 3D printed house in Germany. It's not a very big one. It's about 1,600 square feet, a double decker. Now, at this point, don't ask me how they did the slab. That's a closely guarded secret, because that would require me working against gravity. So we are working on these things. It's not a perfect solution yet, but nevertheless, you see that this entire structure was erected in record 5 days. So basically, this entire structure came up in 5 days. We're gaining in speed. The other thing you notice is that we don't have anything that is rectilinear. The curves that you would see if you had to do these particular construction would take a lot of time. Something even more innovative came out in Italy recently, where they've actually printed these adobe structures. And you notice the shape of the structure. So this is basically clay, compacted clay. Right? Going back to traditional construction, look at the shape that we have here. The shape is basically like a dome, and if you look at dome, it's basically a very nice stable structure. The entire material is in compression, and we have built enough domes and arches in our historic structures, and basically they've replicated the same thing. The construction with adobe is, well, clay and soil are considered a precious resource here. In other countries, they're not so closely guarded or not protected so much. So for them, it is something that they use for construction. The point is to bring back traditional construction, go back to traditional forms. And the reason why we are not doing these traditional forms is because of labor. Today, to get somebody to build a shape like this would basically require finding a proper an artisan who can do this for you. So the whole process, the cost goes up. So we abandoned some of these structural shapes, which we know are inherently very strong, very stable, very stiff, but because we just don't have the expertise or the wherewithal or the labor to deliver on this. But with printing now, I can deliver this, and you can see the video here that this was printed, and you can provide all kinds of surface features. One of the, why Europe in particular is looking at Adobe very seriously is because it has this breathing capacity. So when you are in a Adobe house, the humidity inside is maintained at a constant level, which is comfortable for the human to be there. And also the temperature inside the Adobe construction. If you've ever been to an older construction made of Adobe, it's very comfortable. So they are exploring this very, very seriously. And in our neck of the woods, a guest house was printed. This is done by Twasta, of course aided by IIT Madras, and now this has become, now they're going to take on to this. This is an example where it has come into housing. And now, of course, there's talk of scale up. Now, what is the 3D printing process itself? What we have is, like I said, first we have the digital representation, the layer by layer representation of the structure that is stored in a computer. That is transferred onto this printing setup. Concrete itself is mixed in a conventional manner. You use a drum mixer or a pan mixer. It's dumped into a pump. Then it is pumped to this, what we call a placement system. And I'll show you a few placement systems here. We can have a robotic arm kind of a placement system or a gantry type system. Basically, the purpose of this system is to put material where it is required. That is what this placement system does. The pump is basically just any pump that you would use for pumping concrete. It's a delivery system. So you have a material delivery system, a placement system, and then basically a printing platform where you're creating the structure that you want to create layer by layer. Right? So now control is required at this stage here. I have to control the volume of material that's being pumped out. I need control for this fellow so that that positions the head where it is required. And both of these have to be perfectly synced. So whatever material is being pumped out, whatever volume has to come out here, has to be programmed here so that whatever is the lag, that is accommodated for. And that is basically what the beauty of this whole programmed system that we are able to deliver. Now, this is the robotic arm placement system. Basically, the robotic arm is very similar to as what you would see in any fabrication systems where you have car assembly going on. It's the same system. Or the larger systems that have come into being, and this is basically printing of a silo that is taking place. And these are the gantry-based systems. So basically, the print head is suspended on a gantry here, and the gantry can be raised. So now people, in fact, here, I think in the Middle East, they've printed silos which are almost 50 meters in height. So you can basically just keep on raising this, and you notice something here, that it's actually not a solid system. I can basically create this waffle kind of a system. That's because I really don't need all this material. I can optimize and give you this honeycomb structure that you see here that gives me very good resistance at low use of material. So in this process, I'm actually saving material. Right. So robotic arm itself, there are different, a few types of robotic arms, and usually the way we look at a robotic arm is by looking at the degrees of freedom that the robotic arm provides. So you have a 3-degree of freedom robotic arm or a 6-degree of freedom robotic arm, and this is technology that we essentially borrow from the manufacturing sector. The gantry-based ones, like you see here, so basically, one of the things with robotic arm is that you're limited by the reach of the arm. So whatever is this reach that the arm can provide, that is the size of the structure that you can print. So how do you then make this robotic arm print a larger structure? This would have to be mounted on a mobile base like you see here. So I can actually move the robotic arm. So to print one place, go to the next location, print there, and keep on doing that. So in a robotic arm, what you get is a much finer resolution, much higher fidelity in printing, but then you have to be able to keep on moving the base. And so this requires additional machinery, additional control mechanisms, because now you're talking about controlling the base itself in addition to the controlling of the arm. Whereas when you do a gantry system, you can erect a gantry. It's just like scaffolding that you would do on site. You see, this is a massive gantry that's been erected. This is the print head here. And you can essentially just raise a structure. It's almost like slip forming that you would see on site. You're basically raising the structure one layer at a time. Now, what are the challenges with this 3D printing? One of the biggest issues we have right now is integration of reinforcement. Now, when we're talking concrete and you talk tensile capacity, you need reinforcement in there. Right. So now people are working on this integration of reinforcement, which brings in additional robotics into play, or be clever with the use of the way the steel is placed. The other challenges, and I'll go through all of these challenges one at a time. One, the biggest challenge is determination of structural performance. And I'll illustrate this with a simple example. One of the biggest problems we have is material anisotropy. Basically, it doesn't behave the same in all directions for printed material. Then how do I link the material property to the structural behavior? That remains a big challenge. And then the other challenges, like in any concrete structure or in precast structures even, continuity between structures or structural elements. So here I have an additional complexity is when I talk about continuity in structures, I have to worry about continuity between the layers. So layers are simply printed, deposited one on top of the other to make sure that there is stress transfer that can take place between the different layers. So that in itself is a challenge. And then between the different components, suppose I was to print one component, another component, how do I integrate them so that they act as one structural unit? So these are all the different challenges, and people have come up with clever solutions. One of the things that people with the form-free construction, what is happening, inserting of reinforcement, is that people are talking about co-printing of steel with concrete. So when I say co-printing, it's not hot printing, but essentially take steel wire forms and bend them to conform to the contour shapes that concrete gives. But then now you're talking about two robots that are acting in tandem, one which is shaping the steel, the other which is placing the concrete. So that's something that is really highly advanced, because now you're talking about a bunch of robots that are synchronized, and they have to do their synchronized dance and play, because if one of them skips a beat, then everything goes for a toss. So this is really highly intensive in terms of control, electronics, etc. The low-hanging fruit is to say, fine, I'll use the 3D printing and print formwork. So basically, I'll give you a shape which is not rectilinear, and then you insert your reinforcement, pour regular concrete. Now you may ask me, why then bother with 3D printing? Is I'm not limited to rectilinear shapes. That is the one advantage that I get with this printing system, is that I can give you some non-rectangular, non-rectilinear shape, and you can insert your reinforcement and cast it. So the reinforced concrete structure that would be inside this printed structure, where the printed shell itself acts like stay-in-place formwork. The last thing is to use fibers. Is why instead of using external reinforcement, why not do internal reinforcement, put fibers in there, and cleverly use fiber reinforced printed elements as structural elements, because they'll have tensile capacity. So different methods people have tried. One of the simplest ones is to basically create a steel template. So you'll basically preform your steel and print around it. So that's the simplest thing. More complex ones where they print one layer, then use a wire, high tension wire, to basically wrap up the inner shell with the steel reinforcement, and then print an outer layer around it. So this is again two robots, one that is printing concrete, another one that is putting the steel, and then another concrete robot comes and finishes the job. Third one where they're looking at cleverly placing fibers. Now, if you look at fiber reinforced concrete, and suppose I have a mix where I've added a certain amount of fibers, again the same issue comes. Why should I add full fiber dosage at a location where it is not needed? And if you look at a beam, the high tension requirement is going to be at the soffit, that too near the midspan. Right? So that's where I would need high fibers. So whereas in the other locations, I really don't need fibers. So there is this methodology that has been developed where they basically insert fibers at the last minute, just before it's coming out of the nozzle, based on the location. So you can actually, you have a fiber reinforced concrete mix, except the fiber dosage is controlled based on where the material is being placed and the tensile demand at that particular location. Then this is the Swiss group at ETH that's working on it. So you have this massive robot that goes around preforming the steel, and then there's another robot that does the concrete printing. So it's basically a dance between two robots that are controlling the steel form and the concrete form. All of the ETH, yeah. That's where, to give you a reference, Einstein had parked himself for a few years at ETH. So it's considered the MIT of Europe. Yeah. Now, the other way is basically they have this robot that comes around, and if you've ever seen this in action, it's like the concrete robot goes and does its job, then this robot comes and literally inserts steel into that. So you see this thing is actually literally pecking the concrete, inserting steel rods at different locations. So this is, again, these are all trial systems. People are proposing, suggesting, working on all of these things. There's a split nozzle system where basically the nozzle itself is split, and then as the concrete is coming out, you have this mesh that kind of stays in place, and so the mesh also gets formed as the nozzle gets dragged around. So this is again another system that is used for placing reinforcement. These are all experimental systems. At this point of time, none of these is proven except for laboratory based systems or small structural elements that have been printed. Now coming to the next thing, where we talk about continuity in structures between layers and between different components. So when we talk about this, one of the things to talk about is when we are printing in layers. Suppose this is my whole print contour. So what is a print contour? Print contour is basically the path that the print head would take in finishing one level or one layer. Then the print head rises, which is exactly synchronized to the thickness of the layer. So it rises to the thickness of a layer and prints the next contour. So when you do this, by its very nature, you introduce a time gap between the layers, right? Why? Because even if I wait for one lap to be completed, there's a finite amount of time gap that is introduced between the different layers. So when we look at time gap between the layers, I have the short time scale, and within the short time scale, if the geometry that it's printing is complex, it may take a few minutes for the nozzle to come back. So that is a gap that is introduced, right? Then sometimes, or oftentimes, what happens is, suppose I want to print up to 1 meter height. Now, I can only put so much material into the pump. So I have to, after that material is used up, I need to recharge the pump again. So there is a small amount of gap that is introduced because of material loading. Again, that's on the order of a few minutes, right? So what is happening is layer to layer gap can come on the order of a few seconds to a few minutes, which is what we call the short time scale, which is all introduced because of the process. Right. The other one is a long time scale, which is basically you take a break. So you say, fine, I printed for the day, I come back tomorrow, I print the next, whatever has to be printed on top. So here what happens is you clearly form a cold joint. This is basically not unlike what you would see in regular concrete construction. When you take a break, you come back the next day, you have a cold joint. So you have to deal with both, and both of these have implications when it comes to continuity, right? Continuity of stress transfer between the layers. Now, so people, like I said before, have looked at this procedure where simply a robot comes and inserts this steel wires. So this is a printed assembly, and the steel rods are being inserted while the concrete is still fresh. What does it do? It essentially stitches these layers together. As you can see here, the rod has penetrated through, and it gives you that continuity of stress transfer between the layers. Now, what kind of stress transfer? We will look at it a little later. Then this pre-stressing has been used a lot. And so to produce continuity between elements. And that's where the tie-in comes in with precasting. Right? Except we use a slightly different terminology. We don't call it precasting. So the two ways that I could print a structure is like what you see here. This is on-site printing. So I erect a gantry system there, and I print the entire structure. Right? So this is on-site printing, and this would not qualify as a precast system because essentially it's being fabricated in real time. But we have predominantly what we've been doing is this off-site printing. We call it off-site printing just to distinguish ourselves from precast. We don't want to call ourselves precast.
Precast also, no, they set up the plant on the site.
Well, this is off-site printing, and the reason why we are deliberately using a different terminology is because with precast, you're still stuck with rectilinear forms. I am not. And I'll give you examples of where that can be taken to an advantage. So while it is still precasting, it is not casting, it's printing. So therefore the term printing. And offsite, because even if I have a printer that's perhaps sitting here, it is still involves transportation. So that's why it's called offsite. So I would actually print a structural element and take it to the site and assemble it. Which means, of course, that I'm looking at something very similar to what you do in precasting, where these printed elements have to be brought together, and I have to ensure that there is stress transfer between these elements. And that is then the work of the designer, structural designer. So first, to assess the strength of the printed element, whatever it is, I could print a box section, if you want, of a bridge. Now, where do I gain in 3D printing as opposed to precasting? If all your sections are the same cross section, you gain in precasting. Precasting is all about volumes, otherwise you will not have any advantage of precasting. Right? You could use, if you use the same formwork repeatedly 100 times or 200 times, that's where you make money in precasting, right? If I told you every single segment is different in geometry, you're stuck with precasting. You can't do that, right? Now, the question is, why would every single segment be different? If I actually structurally optimized it, it will be different. Right? So unless every single span is absolutely identical, then you run into the problem of having repetitions. But otherwise, if I was, let's say, doing a one single span or two span and both spans were different, if I optimize both of them, the box sections that I would get would be very different in both spans, and precasting is not going to work. Right? That's where I could print these elements and give them to you. Right? So now the question is, how do I then ensure continuity? So one way to do it is basically print this formwork. So I could give you the shell, which basically looks like a box section, box culvert of or a box girder. And then I could leave places for you to put your reinforcement and simply grout it. Right, so that's one way to basically bring in the structural elements. So this just acts like a shell, and I'll give you enough places in there to put your structural elements in there. Right? The other clever hack is, or basically this is just an example of what we've done of upper offsite printing. You see these double skid walls, and if you actually pay attention, some of these we've left rectangular hollows, which basically allow us to put conventional reinforcement and cast columns. So what do we have? We have these walls, which are basically not structural walls, although we found out later through testing that these do have adequate structural capacity, but we are not relying on the wall to provide structural capacity. Instead, what we're doing is that you see here, we've left a rectangular hollow there, put conventional reinforcement, fill it with concrete. So the main structural system happens to be these rectangular concrete columns, which would then be taking all the load, and these essentially serve as non-structural wall systems. And this, what I gain from here is non-rectilinearity and speed. I could print these very quickly. You could take them to site. As you can see, these elements are being lifted, put in site. You put your conventional reinforcement and you're ready to go. So now, of course, there's a lot of redundancy in this system because I'm using walls which I'm completely ignoring the in-plane strength of those walls and relying totally on this cast in situ elements. But of course, I'm also gaining continuity that comes about from this RC elements that are being cast on site. This is a very clever hack. So this is what I meant by saying, look, these are the bridge segments. Right? Each of these segments is printed. Each segment is of a different geometry, single span, so there's no question of reusing any of the segments, and you can then post-tension it for continuity. So basically, each of these elements is brought together. Each element is about 1 meter in length. You stitch them together by applying post-tensioning to it. And so this is a very smart way in which I can use this. Now, here you may say, well, you do have these printed layers. What about the stress transfer between the layers? The minute I put PT, everything goes into compression. So basically, you're using concrete where it is the strongest. So these are basically the different ways that we are exploring. And like what I wanted to emphasize here is don't take a gun to a knife fight. So we are not going to go and compete with traditional construction. That's not going to happen. We'll get beat black and blue out there, because the traditional construction methods have been optimized over a century, and everything right down to the cost has been worked out to the lowest decimal point in the cents or in paisa. Now, that is not going to happen. What is RMO then in printing? Is that I can give you systems or a structure where every element is different. I can precast or pre-print it for you, off-site print it for you, give it to you. You can assemble them together, create a structural system inside the printed form, the shell that I'm giving you, and have a precast structure. That is the advantage of the system, right? And that's why I don't want to get into housing at this point of time, because we've tried. Our math just doesn't work out.
But actually, housing is where typically people want to have unique features.
Yes, but those are boutique houses. Yeah. So the minute I get into mass housing, social system, it is not going to work. Because every unit is identical in the social housing that we provide, that is just not going to work out. But yes, boutique villas, you can't beat us. So, but what you have to be clever in this whole system is figure out a way to embed the structural system inside. That has to be done. Whether you can take advantage of the printed form itself as a structural element, if you have enough confidence to do that. And at this point, with available knowledge, we are not yet very comfortable with using this completely as a structural system. So what are we doing? We're basically resorting to redundancy, where we put a structural system inside the printed form and say that is going to take the force, unless you come up with a compression-only system like this. Here, what you're doing is you're compressing it. So here, and the beautiful thing here, and I'll play up on this concept a bit more, I'm using a self-equilibrated system. Here, concrete is in compression, steel is in tension. So basically, both of them are nicely self-equilibrated, right? That's what typical, PT structures are all about. And I'm playing off to the strengths of both materials. Steel takes tension, strong in tension. Concrete, compression, strong in compression. So basically, I'm taking advantage of where the two materials are the strongest or perform the best. And I'm basically able to print these different shapes, right? Which are, every shape here is going to be unique, as you can see here, right? And give you something that is actually what we call form optimized. So here, the usage of material compared to conventional structure is much less. When I talk material, I'm talking concrete. Okay? So that's where this particular technology is a winner, and it can be applied in precasting. Of course, we call it off-site printing, right? Just to distinguish ourselves from precasting. Right, the next thing is, sorry. So now talking about anisotropy, I'll spend a little bit of time on this anisotropy. And so here's what happens. Suppose I print, so if you can imagine, this is the thickness of the printed layers made up of multiple layers. So what I have done here is I printed the first set of layers, taken a break, a clean break, and then I print the next set of layers. So if you can imagine this here, this is printed, made up of multiple layers, a break here, and then another set of layers is printed on top of that. Then what was done is, this is the top view of the structure. It's a rectangle that's printed, right? So you have multiple layers that are stacked up. What we're trying to do is basically core through here. Okay, cores were taken. So when I take the core cuts through the newer set of layers and the older set of layers, right? So when I test this in tension, this is what you get. So if I do the direct tensile test of the material without printing it, suppose I just take the concrete, cast a cylinder, do a tension test, I of course get a large scatter, but you can see the average tensile strength is about 3 MPa or so, right? Now, the 0-minute gap that you see here, 0 minute is when I do printing. Whether I like it or not, there'll be some gap that will come about because the nozzle has to go one direction, reverse itself, come back. So a few seconds will always be there, right? So that time gap is basically the natural time gap that you get for the traverse of the nozzle going back and forth. If you look at this, even with the 0 time gap, you see the drop in the strength. It's already dropped. So these printed elements, if I was to test across this is the newer set of layers, this is the older set of layers. If you do a tension test of that, the tensile strength is already dropped significantly, almost 30% drop is there, which means the interface between the old and the new layers is not as strong as the parent material. That's the first thing we learn, and that's expected anyway. Right? And that has consequences. Now, if I wait longer and longer, suppose this is the short time break that I get 15 minutes, you see that there's a nice drop here. To the point that if I come to a few hours where I get into the cold joint area, the tensile strength has dropped significantly. This is a major concern because, of course, we have the same concern even with cast concrete, but this is reality for me. Now, if my traverse time, suppose the contour is very complicated and it takes a few minutes, then I'm already looking at a drop of almost 40%. Right, compared to the parent material. And this, if you look at it, is made up of multiple layers. So what I have here is each one of these interfaces is a weak link in the system. So if you look at this printed assembly of layers, if I ask you what is the tensile strength of the material, which one would you report? Would you report the strength of the filament, which is basically the extruded filament, or the interface? But of course, as engineers, we'd say, well, the tensile strength is going to be whatever I get as the lowest value. So that would be the strength of the interface, and that is not nearly enough to qualify for use even for concrete. There are other problems too. Because we have these interfaces, so you see, if I try to look at moisture ingress or chloride ion ingress, you see preferentially the chloride ions start getting in through the interface. So interface is like really weak. It not only is structurally weak, strength-wise, but also from a durability perspective, this becomes a problem. So what we did is that we actually printed these elements, which are like a large donut-shaped elements, and from there we extracted beam and cubes from them, and we tested them. So let me show you what happens when you test them. Now, we have to first, because we're dealing with something that has some level of anisotropy, we identify material direction. So if you look at it here, U is the direction in which the material is being deposited. So this is the print direction that is labeled as U. So along the print direction, you identify that with the material direction U. Then you have the direction V, which is perpendicular to the interface, and material W, which is basically across the interface. You're basically flattening the interface in W. So you have three material directions that you can identify here. And from the printed assembly, if we were to extract cubes, standard cubes, and test them, what we find is the strength is significantly variable. The material is the strongest in the U direction, right? And it is the weakest in the V direction. So when you start testing it, suppose these are my printed filaments with these interfaces. If I test them in the direction of the deposition of the material, that's where it is the strongest. If I test it perpendicular to the interface, that's where it is the weakest in compression, right? So mechanics, yes, has to be still put in place, but that is what we're dealing with. So now, if I was to port what I know from my structural mechanics or what we know about strength of concrete, what would we do? We'd say, well, as an engineer, let me be conservative. Let me take the strength in the weakest direction, which is 38. And this is the average strength, and this was obtained by testing 13 cubes, so I have enough data there. I can actually estimate what is called the characteristic strength. Now, what is the characteristic strength? It's 1.65 times the standard deviation removed from the mean. If you look at this 38, remove 1.65 standard deviation. Standard deviation is also given here. And when you actually work out the math, the characteristic compressive strength in the V direction comes out to be about 30 megapascal. Okay, so as an engineer now, can I treat this as if it is concrete of 30 megapascal strength and design it as if it were a cast in place concrete, right? So that is the next question. If I really want to take it to a codal level, I have to be able to go to that level, right? And I'll answer it.
Quick question. See,
Yeah.
Again, let's say if I'm printing a very long structure, that also will influence, just like you
Absolutely,
said.
absolutely, yes. So when I talk about cold joints, it's a whole different scenario altogether.
Compression also it will have.
Compression also it will have it, right? This is basically going to repeat itself. Only with zero time gap, this is what we're seeing. Now, if I increase the time gap, it's only going to get worse.
Typically, silos and
Yes.
it takes you plan it with multiple.
And so basically, suppose there are two things here. Suppose I can translate the whatever is the time of transit into some strength measure. And we know that always the U direction is always the strongest. Okay, suppose I was to get the, and we know that V direction is always the weakest. Okay, which is basically when you're testing perpendicular to the layers, right? Now, if I keep that orientation in mind, right, if I can somehow translate these time gaps into strength reduction, then can I still use this? The whole point is that suppose I give you the strength in V direction, however it came about, whatever the time gap. Is it reasonable for me to use this characteristic strength I get from here, and which I calculate to be 30 megapascal? Is it okay to use this in structural design? Now, as an engineer, we say, well, I'm conservative. I've tested 3 directions. I'm taking the lowest compressive strength. So what's wrong? Everything. So I'll just show you what can potentially go wrong.
Eventually, we need the strength only in the vertical direction.
Well, that's okay. But what I'm saying is, suppose for now I put on my cap as a designer. And I say, well, I've tested in the 3 directions. I take the lowest characteristic strength from the direction where it is the weakest and pretend as if it's the same strength in all directions. Am I conservative?
I expect so.
Right? Okay. So
Except I'm a bit worried about the creep effects.
about the, oh my God, you're going to the very high scale. We are not even there yet. Okay. So let's see what that does. But here is my problem. One of the problems that I have is that we are set in notion that we have been taught for concrete that the tensile strength is about 1/10 of the compressive strength. 30 megapascal. If I test the split tension of the filament, so I basically split the filament, then the tensile strengths I start getting are about in the same range. About 3 MPa. If you look at it, this is the tensile strength. About 3 MPa is what I'm getting, which makes sense. If I try to split the interface, the strength is abysmally low. It's about 1.75 or so. So now, if I want to continue using it, treating it as if it's 30 MPa in all directions, first thing I have to do is to translate that and come up with a new relationship that gives me the tensile strength, which is not your 7.5 square root of FCK. I have to come up with a new relationship, which will basically be much lower than what I get from my regular concrete design equation. Regular design concrete equation would do a fairly good job when I look at the tensile strength of the filament, but does a horrible job when it comes to the interface. Now, I'll basically quickly run through these slides where we tried this experiment with different grades of concrete, and we see that the anisotropy always repeats itself. So you see the compressive strength with different grades of concrete in the 3 directions. So that is U, V, and W. The 3 colored bars are for 3 different types of concrete that are printed. Always the U direction is the strongest, V is the weakest. That pattern repeats itself. And the tensile strength, this is what you get with the 3 grades of concrete. Now, if you look at the compressive strength, so let me go back to the compressive strength, sorry. If you look at the compressive strengths, we're talking about numbers which are even touching 50 megapascal in the strongest direction. The weakest direction is also around 30 megapascal, right, for the 3 grades. I would expect tensile strength to be around 3, roughly. What I get here is actually this. Horribly low, right? So which means that if I have to extend what I use in regular concrete design, those conventional design equations will not work because my interface is so weak, the material is going to be very weak in tension because of that interface between these 2 layers, unless I figure out some way to deal with it. So this is the split tensile strength that is expected, which is usually in the range of 2.1 to 3.5 of FCK percentage, and then this is what we end up with, much lower than what we would expect from there.
It's more like a compression tension.
Sorry?
Weaker properties in other direction actually reduces your compression.
Reasons are manifold. The question is, how do I port what I know? So if you're a designer, then how safe are you if you just treat it like a concrete of 30 megapascal compressive strength, which is assuming that the strength that I get from the weakest direction is what I get in all directions, right? So how safe are we? Well, first I have to address this issue where I have to come up with alternative math, alternative equations that give me tensile strengths, and the tensile strengths are very low to the point that I may have to completely neglect it. Okay, so that's the one thing. Flexure is surprisingly robust. It is not sensitive that much. So if you actually get the flexural strength, it's not very direction variant. That's the one thing we see. And that's because the layers really don't play that much of a role when it comes to flexure or bending. Whether you're bending in one configuration or the other, it really doesn't matter so much. Now, we worked on improving the interface. We looked at different sprays because that's all you can do. And we use conventional bonding agents. So you have the styrene-based bonding agent and the acrylic-based bonding agent, two conventionally used bonding agents, which are typically used when you get a cold joint between two pieces of concrete. Now you see that when we do the split tensile strength, our numbers are starting to get respectable. So now, if I really want to port what I have done using the conventional wisdom, where I take the concrete compressive strength in the weakest direction, then numbers are now coming into the expected range of 7 to 12% of FCK, and I can perhaps now start using what I know from my conventional concrete design, pretend as if it is a concrete which has the lowest compressive strength of all three directions, and that is the compressive strength in all directions. And now the tensile strength is cooperating with me if I start treating the surface layer with, say, any of these methods.
Now, in the conventional concrete cold joint, we specify that the surface should be intentionally roughened so that there is a proper adhesion.
Proper adhesion, yeah.
Now, is there some possibility like that?
That's also being explored. So basically, we're trying to roughen the surface up as we're depositing it, so that the mechanical aspect of the bond is also improved, right? In fact, we had done some part of this here, where we did roughen it. Despite that, it didn't tremendously improve the tensile strength.
There are no pores in place.
There are very few, right? So we go up to max 4 mm, so there are much fewer. Flexural strength, again, we see an improvement. So coming back to this whole equation, if I look at this layered stacked assembly of different filaments, where U, V, and W are distinct directions. U is the direction in which the printing is happening, V is perpendicular to the layers, and W is basically where you're compressed across these different layers. So W is where you're basically perpendicular to the layers. This is along the layer interface, and this is the print direction. So three different directions that we have. So now, is it okay for me to design with this printed assembly as if it has compressive strength in the V direction, which is the weakest direction? So you have the printed filaments and you're getting the compressive strength in this direction here, where you're basically compressing perpendicular to the interfaces, right? I'm taking that as the compressive strength of the material. My tensile strength, I can raise it up to 7% with some kind of surface treatment. You just saw that in the previous slide. Flexural strength, this is fairly okay, 0.7 root FCK. And my chloride penetration, although I didn't show it to you here, and moisture penetration can also be improved with the surface treatments. So now, is it okay for me to start using my conventional design procedures, pretending as if it is concrete with a compressive strength, which is in the weakest direction? Our conventional wisdom will say, yes, it's okay, but, there's always a but. Let's look at this. Suppose I look at a complex state of stress that I subject the concrete to. Now, how do we understand the behavior of concrete? Concrete doesn't understand shear. Concrete only understands compression and tension. So if you're given any complex stress state, first thing is to look at the principal stresses. Concrete behaves a certain way in tension, a certain way in compression, and it's a combination of these two that dictate the behavior of concrete, period. So if I look at a homogeneous piece of concrete, homogeneous would be cast concrete, then basically what we do is that we translate it into the stress state into the principal stresses, principal compression and tension, or principal compression, or principal tension. And knowing the behavior in each of these directions, in compression and tension, we go ahead and predict the response, right? Now, here I'm essentially at some level trying to separate the behavior of concrete in compression and tension. But see what happens when we start with a printed assembly. I take the same stress state. Now, when I transform the stress, what happens is I get the principal stress state, but the material doesn't rotate, right? The stress state has rotated, right? The material is where it was. So what happens now? Now, even if I rotate this, what I cannot avoid is this. My interface would still be subjected to tension and shear or compression and shear, right? That is not my worry here. Because of the anisotropy, what happens is that because of this structure here, I end up with a stress state on the interface, which will always have some tension and shear or compression and shear.
That's the problem with the masonry structures.
That's exactly where I'm headed, actually. So, so that's exactly what happens. And so, if I was to port something like your favorite modified compression field theory, or I forget now, soft thrust theory. so, apologies. I had to take a poke there. So there, what do? This is what we do. We pretend this doesn't exist. We start operating in this domain here. I can't do that here because when I go down to the micro level, this is what awaits me. And I cannot treat it like a homogeneous material. I have an interface, and therefore understanding the behavior of the interface in shear becomes very important. Either it's pure shear, shear plus tension, or compression plus shear. This has to be understood. And as correctly pointed out, we have to go to masonry. So we have elements, materials that we've been using for centuries, which have these natural joints. Same problem happens there. Suppose I have a masonry. Right? Now, masonry has vertical and horizontal joints, and if you try to transform your stress field, what happens? The material doesn't rotate, so you end up with exactly the same problem as what you encounter in masonry. So that is where we are headed, and what you need to understand is the behavior of masonry, or port whatever we know from there, where basically you try to understand the shear transfer across the brick units when you have different levels of compression or tension acting in the perpendicular direction, right? So you could do something like a triplet test, which is typically done for masonry, to understand what is the stress transfer happening across this interface here, right? And you could actually come up with, we've done this work, a lot of work in masonry, where we looked at shear transfer across this joint here. Of course, now I've switched my gears, I'm talking about masonry. But just to explain to you that if I have two blocks of masonry, these could be three filaments in fact. Printed filament 1, 2, and 3, and this could be the interface that forms between them. It's exactly the same mechanics. So if I actually understand the behavior of masonry, and this is coming from masonry, here we've done masonry tests where we're looking at shear transfer at different levels of compression. Now I can come up with constitutive theories. I will not bore you with this, but then enough micro level models are in literature, where you can port from plasticity, you can use different formulations where you essentially go down to the Coulomb's friction mode of failure, which is basically a combined shear and compression, compressive stress failure. And you can formulate a failure surface for the masonry. And just like what we would do in masonry, here I'm gloating a bit because we've actually done the simulations for masonry. So you see what happens with masonry. So if I have a masonry wall, subjected to compression always, because a masonry wall will always have some load on top. So this is always guaranteed if you have to take a masonry panel, and I subject it to in-plane shear. You can actually, by understanding the behavior of the interface here, you can actually formulate, essentially predict the behavior of this panel in pure shear. Same mechanics can now be ported to the case of printed elements. But what I need to do that is to understand the behavior of the interface under pure shear and combined action of pure shear and compression or tension, right? The mechanics is already there. I just have to simply take this mechanics that's there, port it to the case of printed assemblies. And of course, we've done it for different cases with different levels of compression for masonry, just to show you that it can be done. So, what are we talking about when it comes to printed structures? Well, we have this structure which is made up of layers. Some anisotropy is bound to happen. The reason is I have these layers. So now the stress transfer between the layers becomes very important in determining the strength of the printed filaments. And as I concluded in the last few slides, it's all about the shear stress transfer across those interfaces that are formed between the printed elements. And we can go down to that level and start coming up with predictive equations. Now, whether we can do the same, port the same mechanics from cast concrete, that I think is going to be unconservative at some point, because it does not address this issue of shear transfer across the interfaces, right? So, whether we can treat it as concrete, as having the printed filaments as having compressive strength, which is close to the compressive strength in the weakest direction, and port all our design equations around that, I think no, that would be a mistake.
Is anisotropy also time dependent?
Yes.
That means if you are having some durability issues, will the anisotropic factor increase?
Absolutely. So it should, just the same way as it would in concrete. So even concrete is a chemomechanical material. So when you have degradation, it affects its performance. Very similar, except here the degradation will happen preferentially at the interface. That's my weak link, right? So absolutely the same set of mechanics. So if we are going to look to developing design equations, I think masonry is our friend for this case. Okay, and we probably would have to borrow from masonry, learn or adapt from the masonry code to come up with codal equations for the use of this printed elements. Okay, how am I doing time-wise?
When is the tea break? How much time you want?
You give me any amount of time, I'll go on. I'll keep jabbering. So
You take a break and come back. You half an hour you eat or not?
either way, half an hour.
Then we'll take a break and come back.
Or you want to come back after the break?
No, I think we can finish it.
Yeah, coffee won't get cold, right? Tea or coffee? Okay, fine. Yeah. So I see some restless people here. So would you rather take a break? Okay. Yeah. So what I want to demonstrate is something which is a little bit more interesting, which, oh, my friend is gone, where I want to demonstrate that how can we use this printing by taking advantage of the shapes which give us naturally very high resistance. What do I mean by that? Why is it the structures that were built millennia ago are still standing? Right? And they were building using one of the most brittle materials known to man, stone. The reason is somehow implicitly they understood that material is brittle, but the assembly of materials need not be brittle, first thing, and can be made to behave in a composite manner in such a way that you take advantage of where the material is the strongest. Now, typically brittle materials, you will see a big difference between the compressive strength and tensile strength. Now, that is what fundamentally separates brittle materials from ductile materials. If you look at steel, you'll get nearly the same yield stress whether you're doing tension or compression. That doesn't happen in brittle or quasi-brittle materials, glass, right, stone, concrete by extension then, right? You get very different strengths in compression, very different behavior in compression as opposed to tension. Right? So now how do you deal with such materials is to take advantage of the shape. So this is something I'd like to gloat about as a bridge that we put on our campus. It's a 7.5 meter bridge, right, that was printed. And what I want to go through in the next few slides is the exercise of what we call form-specific structural system optimization. What I want to do is to play off on the shape. And I'll describe that to you. And within that shape, which essentially keeps concrete in compression, I want to do a structural optimization. That is, I have the liberty of putting material where I want. Right? Wherever I put material, it's concrete essentially, that becomes a structural element. Right? Now, can I put material in such a way that I get a lightweight structure where the material is used optimally and efficiently? Right? Now, suppose you had to design a structure, right? When do we call the structure as efficiently designed? For me, the measure is, if I was to calculate the difference in the stress, right, between the highly stressed point and the lowest stress point, if that difference is large, that means it's a very inefficient design. For me, an efficient design would be if I'm able to reduce that difference, and most efficient design would be when there's no difference between the highest and the lowest stress material. That's when you know material is being used most efficiently. So what happens when you are able to equilibrate the stresses or reduce the differences? Now, when you reduce the differences, what is happening is that I'm using all material efficiently. That means that I can actually remove material where it is not needed. And that is what we're going to explore here through this exercise. So the printing setup, we were using a robotic arm system. I won't dwell on this much further. But the structural system is basically came out from the idea of a tied arch. Right? So what is a tied arch? These are actually copies from my notes as I was making when we were going through the exercise. In a tied arch, you have basically an arch, which could be concrete, it could be stone, it could be masonry. But if you just have an arch, what happens if you apply a load on top is that the arch will tend to open up. at the bottom. So this would basically tend to open up and it will eventually fail. You need to hold the ends together, and so you need the tension element. So what is the best system you can create in a tied arch is this. So I put this in concrete, I tie these two ends with a steel tie. Now what I've done is I've created a self-equilibrated system where I'm taking advantage of the fact that concrete is strong in compression. So this can be made of concrete, and this is the tension tie, and I've separated out the compression and tension. In this process, if you look at the stress in the arch, it would be nearly uniform. Right? If you load an arch, and it's a perfect arch, you'd find that the stress difference between here and here would be quite small. So that means concrete is being used where it is the strongest, and the stress in the concrete is also nearly uniform. Right? Some of the best bridges that were designed at the turn of the 19th century by the British were made of masonry, and they're all arch bridges. And they're still standing today. Right? And the reason is we are using material where it is the strongest. They're masonry structures. They're taking the traffic of 25-ton wheel loads that we are operating with the railways today. Now, so initial concept was this, is I make this out of concrete, but why make it solid concrete? I'll take out material wherever it is not needed and come up with an optimized shape. Then as we started working on the design, I was told that, no, you can't have a bridge like this. Who the heck is going to climb on top of this and come down? You give us a flat riding surface. So then the exercise changed to coming up with the same arch geometry, but from a beam design. Now, and these are literally from my notes. So basically the idea was that I'd print here, so this would be my direction U, right? My V direction would be in this direction here, and the W would be basically going into the plane of the board. So that was the idea of this printing. Right? So what am I achieving with this? I'm aligning the strongest direction of the material with this, with the structural element, right? And the weakest is going to be perpendicular to the board. So basically the weakest layers would be stacked up behind, going out and inside and outside the plane of this board, right? So now the idea was to come up with this compression form. Now if you do a finite element analysis of a beam, rectangular beam, subjected to UDL, you'd find, if you just plot the stress contours, you'd find that these catenaries, right, are formed inside. The stress paths form catenaries, and you'd find that the top part of it is going to be in compression. Of course, it's simply supported here, and the bottom part is essentially all in tension. Right? So the first immediate thing is, why have the tension part? It's not doing anything, it's adding weight. Take it out. Right? Now, why do we not do it in regular construction? I'm stuck with a rectangular formwork, so I'm going to dump concrete all over, whether you like it or not. Now, you can actually remove this entire part, which doesn't really contribute much to this, and you get this compression form with a tension tie, right? So this is my starting point. And then, of course, to develop a structural system inside this compression form, this is in the compression form, there's several ways of doing it. What people, oh, I'm sorry, my text got scrambled here. So there people follow a process called topology optimization. If you've heard of topology optimization, what we try and do is, it's a mathematical exercise, right? So I can give you this rectangular domain, and you can give it into this optimization subroutine. These are complex optimization subroutines, which will basically take away material wherever the stress is low. And you keep coming up with a revised geometry after every iteration. What comes out of there is something which basically would not necessarily have a regular structure, and the filaments or whatever are those little elements that end up after you remove the material where the stress is low, those may not have constant width. One of my biggest constraints with printing at this time is that I can print filaments of constant width. So we have to take a slightly different approach than topology optimization, where we said what we'll do is take this compression form and go through an exercise of what is called a Mitchell truss analogy, where you try to basically take the 2D stress contour and replace it with a lattice made up of beam elements. And then we try to optimize the lattice. So basically the idea is that this is my compression form. I fit a lattice inside here. Right, it's basically a truss, and then try to optimize this truss inside the compression form. So we've gone through the different iterations, and again, this is important from a perspective. This is one of our first iterations where we developed this lattice structure, It is a three-piece truss bridge. So here is piece, where is my, here is the first piece, here is the second piece which would be printed separately, and the third piece that would be printed separately. The idea is to bring the three pieces together, put the center piece in place, lock the tension tie, you have a self-equilibrated truss structure. Now, if you look at this particular thing, my print direction is going to be along here. How would I print this structure? The nozzle would basically move around, and U direction is basically aligned with this truss element here. U is the strongest direction. So what am I doing? I'm placing my strongest direction where it has to carry the stress, right? The filaments would be stacked up in this direction here. So the weakest direction is going to be basically which make up the layers. Okay, so that is the thing to keep in mind. Now, we've gone through this iterative exercise where we've gone through the starting point here, done the stress analysis for this, then gone through where we've created these nodes. You play around with these nodes which make up the Mitchell truss, and starting with this, we end up with this structure here. This is the final arrangement we came up with. It's not the final, but if I describe the process, here are my variables. The arch height, I can either increase it or decrease it, right? Both have advantages. Then, if I just go back to the previous slide, then if I fix the arch height, it's a two-piece bridge. So this is piece 1, piece 2 with a closure pore, right? It would be offside printed, which means that this would be printed offside, this would be printed offside. We bring them together, put the closure pore, put the tension tie in place, you have a self-equilibrated system. Then within this one piece, I can basically play around with these nodes, which would basically give me a different configuration of the lattice structure every time. Right? So we did a lot of iterations where we iterated with the lattice structure, and the objective was not to compromise in the performance. What performance are we looking at? We're looking at the stiffness of the bridge and the load carrying capacity. What is the maximum load that it can carry?
Some of the diagonal elements have to be in tension, right?
They are in tension, small amount of tension. Yeah. So, and for that we did introduce a little bit of reinforcement. I'll just show you what happens there. So having done that, my biggest worry is this fellow, the top element here. So this goes into flexure, right? This element actually goes into flexure. The alternate elements go into compression and tension. So I cannot completely avoid tension, but the tension is very small in this element. I do need this element. I cannot completely eliminate it because I need it for support, right? So we were able to basically come down to this rectangle with this shape, which basically, if you look at the volume of concrete that goes into it, it's about 23% of the area of a solid rectangle. So I've already optimized compared to a solid block. I've already saved 23% material. Yeah.
So this, the key element has to be little up. Then only you develop the restraint at the bottom. Otherwise, you won't develop that.
No, in fact, I don't have I'm not sure I have it. But if you look at it this way, right? Now, this is what we put as 250 millimeters is flexible 250. And that will be adjusted on the site. So what we do is we hold up these two pieces and then do the closure pore and then remove the support. So,
only the restraint will come.
Yeah. So this is essentially the same technology or the same methodology you use for a masonry arch bridge, where the keystone is always put at the end, and everybody holds their breath when they remove the support. So we went through the same nerve-wracking experience here. When we removed the supports, we were hoping it would stand, right? So this is the this is the final configuration of the bridge. We did cheat a little bit. I'll tell you what I mean by saying cheating. We used a small reinforcement template. So this is basically a wire which is 3 millimeters in diameter, which is bent into the shape of this filament here. And every 8 layers, we would basically lower this steel template onto this. It's just a 3 millimeter wire. So it's basically, if you look at the reinforcement ratio, it was about 0.08% or something. And it was not intended for providing major structural response, but to take care of that little bit of tension that is in those diagonal tie elements. Yes, those are actually addressed at the material scale. So we basically, if I don't have a proper mix where I'm not able to address that, you'll see cracks as you're printing. So that is usually addressed in the material mix design itself.
Have you put any fibers in the concrete?
A little, 0.2% polypropylene, fine fibers, right? But not specifically to address shrinkage per se, right? Now, so what does this 3 mm wire do? We did some tension testing in the form of fracture where we made these fracture beams and just simply put this wire, 3 mm wire, between 2 layers here. So you print 3 layers here, put those 2 wires here, and then keep printing the remaining set of layers. That's what we did. When you do the tension test of this beam with this wire sticking out, it's basically going to replicate what you see with the tension tie, because the wire has simply been put there between 2 layers. So when you do the fracture test of this fellow, we've done the fracture test, I won't dwell on this much. So what happens with the wire is that, you see, if you look at the unreinforced one, what you would do with a very carefully controlled experiment is that you get this typical fracture response of a concrete beam where the crack forms, it grows through the element, and you get a continuous drop in the load. With that 3 mm wire at the interface, which is put between 2 layers, you see that now, after a large crack mouth opening, almost 200 microns or so, you see some residual stress come up. And remember, this is a plain, smooth wire, so there is actually no ribs or anything that is helping with the anchorage, and it's simply dumped there. So we printed 1 layer, put a steel layer. For that itself, we are getting some residual load carrying capacity from this wire that is placed there. And this basically replicates what I do with the template. Remember that we are printing 8 layers, putting a steel template, which was basically had the same centerline shape as what I would get with the filaments. So now with this, we did load testing of the bridge, convinced ourselves. From here, of course, we can also extract the cohesive stress, what is transferred across this here. But then, after we had done the calibration, my students wouldn't let me load the bridge to failure, so that was a failure in itself. But then we were able to load it, we printed a prototype bridge which was smaller, which we were able to load into the nonlinear ranging, although we didn't take it all the way to failure, but that gave us enough information to calibrate our finite element model. So now we have a finite element model which fairly accurately represents what is happening in the structure of the bridge. And with that, we are able to predict the response of the 7.5 meter bridge. So here's what happens. When I start applying the load in the form of a uniform distributed load on the top surface here, at this point, around 30 kilopascal pressure is where I see the first crack develop. The first crack actually develops right here in flexure. Right? If you look at it, it's like a continuous beam spanning across these 2 struts. So this is where I get my first tension crack. And that basically produces small change in stiffness, but the load continues to build. Eventually what happens is that these diagonal ties start cracking in tension. Right? So you see, in going from 1 to 3, which is the peak load, a lot of these diagonal ties are starting to crack in tension. Now, although the tension cracks form in the diagonal ties, because I have that little wire that's hanging in there, it's able to transmit a small amount of tension. What happens in the process is now, this is where redundancy in the structure comes in. So when this tension tie cracks, the stress is redistributed inside the structure. So basically the other elements start picking up in stress. And slowly up to 0.3, what happens is that we see more and more tension ties start to crack. And there is an increasing redistribution of stress that's happening within the structure here. Final failure happens at 0.3, where basically this is, remember, the bottom arch is in compression. The bottom arch fails at compression. You have a compression failure there, that leads to a failure of the structure. So failure is driven by compression of the compression strut. The most heavily loaded compression strut is the bottom arch here. Right? So that's what fails, and that produces the maximum load. And this is the tensile stress. So suppose I had a tension tie running across here. This is the tensile stress that would be required to support the bridge in place. So the required tension clearly builds up, as you're seeing. As I apply the load, the arch is kicking out, and the tensile force that would be required to hold it in place, that builds up. And then, of course, when the failure happens, the load drops and eventually it fails.
One question. So can we not go for remove all the tension members, put steel tubes and bolt it?
Yes and no. So the thing is, initially we designed it as a tension, like a tied arch, to the point that we even printed it, leaving holes so that we could insert these tension ties. And then somebody said, wait a minute, if it's a steel tie, it's going to rust and it's going to fall apart. So then we said, okay, we'll change it to carbon. We'll go to carbon tie. Then somebody said, if you're going to put it on your campus, and the students are not exactly very friendly creatures, if somebody loosens the tie, the bridge is going to become unstable. So we basically eventually transformed it into an end-supported tied arch, where we essentially put the horizontal thrust onto an abutment. Right? But the idea still holds. I mean, the thrust, this thrust that would be taken by a tension reinforcement is now going into the abutments.
But I think there is still further refinement in terms of, bolted systems are very common. So you replace all the tension element, later on you come and bolt it.
We can do that, yeah. So we can actually.
The whole beauty of the 3D printing gets lost.
Yeah, I mean those are things that have to be thought about. I mean, I can replace it with, and the tension in this is not much if you look at it, right? So I could actually replace it completely if you want with alternate tension elements made purely of steel or carbon or what have you. Come up with an alternate functional form, right? But you're right, I mean the beauty then goes away. So I just want to show you the printing of this, if this video works. So I just want to show you how quickly we are able to print. So this is something that's been printed almost to a meter deep. So you see how fast the material gets deposited, right? But despite that, if now the thing was to repeat itself, to come back to this point would take about 40 seconds or so. So that is the time that it takes, the zero time as we call it. And that is enough to create some weakness of the joint interface. Finally, this is what we have installed on our campus. Please feel free to visit this. It's near the first roundabout, first or second.
It's close to the guest house.
It's close to the guest house. Those of you who are staying in the guest house, it's just between TIP and TRP buildings, right? You see the bridge in all its glory, right? And I've upward rounded it. It's actually 7.5 meters. But then when you're gloating, you always try to take numbers to your advantage. It's 8 meters, it's 7.5 meters is the span. So we've done LCA analysis. So just so I don't completely fool you with what I'm doing here, we've actually done an LCA analysis. So what would I do in an LCA analysis? Well, I have to convince you that it's actually a sustainable option. How do I convince you? Well, first thing is we designed the same bridge, which is a 7.5 meter span for the same loading, right? And deliver an alternate bridge. Suppose I gave you a problem where I said, fine, you design a bridge, a pedestrian bridge, which is 1.2 meters wide, right? Over a 7.5 meter span. Now, the best configuration that would work there is a one-way slab. And typically, even in railways, they resort to one-way slabs if the spans are small, 5-7 meters, typically that's what they do. So we've done a one-way slab design for the same set of loads and compared to that. And compared to that, we've actually saved half the weight of concrete, right? So compared to an equivalent structural alternative, I've saved 50% of the concrete.
Also, it is much more aesthetic. That's
Yeah, but the thing is, aesthetics doesn't feed the bills, right? I mean, ultimately, I have to convince people that I'm saving them something, and this is the savings we're talking about. And savings have to be with respect to an alternate structural system for the same performance. And that's compared to that. In fact, I'll be presenting on that at the TLC. We have about 50% savings in materials compared to the conventional design. So there is a lot of material savings to be had, right? Now what we're doing is trying to look at the carbon tag, because these mixes are cement rich. I will not deny that. The reason is aggregates are smaller. Currently we are printing with 4 mm aggregate, which makes the concrete cement rich mix. So compared to conventional, we take double the amount of cement. So whatever savings I have here, if you look at it in terms of cement, although I'm saving the weight by half, because I'm consuming double the cement, it basically breaks even. So the future, if this technology has to catch on, we first have to work on our concrete mixes. And that's what we're currently working on, is to bring down the cement content in the printable mixes. And we already have managed to bring it down. And I see in the next few years, we'll probably bring it down and almost catch up with conventional concrete. Okay. Now, just last few points that I wanted to make is that there are a few standards in this. There are not many, but a few. One of them that has been put out is by the International Code Council. This is the closest that you get to a code. They're talking about 3D automated construction technology for 3D concrete walls. So very specific about 3D walls. And it's a consensus committee, so it's not exactly a codal committee, but they do have some interesting guidelines on how you could use these for as structural walls. The problem here is They admit that there's not enough information. They cannot give you design guidelines. If you want to use it as a structural wall, you do a full-scale test and convince yourself and then use it. How easy is that, right? So that knowledge is still evolving, and once that happens, then we will be able to give you design guidelines as well. Now, not to be left behind, the BIS is also pushing for standards on this. We are a little behind the curve on this one. CED 32, the Prefabricated Construction Committee, is going to bring an annexure to the IS 15916 on 3D printing. Basically, it's going to be a guideline. That's all it's going to be at this stage. And basically, just to tell you all these terminology that I've been throwing around. What is 3D printing? Then what is off-site printing, and how is it different from precast, etc. Okay?
We're also working on it, but it's not going anywhere.
So, no, this one has been kicked from I was in the working on the subcommittee that dealt with this.
But the main 15916,
that I think there are enough stalwarts here who can take it forward. So with that, I'd like to thank you for your attention. This is a photograph from the load testing of that prototype bridge. Yeah, I mean, this was a scary moment when we started loading it up, and the first time we heard a small cracking noise, everybody stopped and we wanted to see what was going on. But then it took a lot of load, actually. We were able to pile these almost 7 layers high, and it was perfectly intact. And if you're still not convinced, we load tested it in the Gyan course that happened 2 weeks back. I think some of you were there, so, and they will tell you, I would say convince yourself, you go there, you can jump on the bridge, you'll not feel any vibrations or anything. So performance criteria are met, serviceability and capacity, and of course even the capacity. So with that, I'd like to bring it to a close. I know you're waiting patiently for your coffee, so I can stop, take any questions if you want, or we can talk during coffee break.
this is the 3D wall panel system for tall buildings particularly. Okay, I'm not able to integrate any reinforcement, but again, I can bond the FRP systems and all, right? So multiple ways we can work with that.
All legitimate options. But you see, the problem is that this is what I see with a lot of naysayers. So FRP butt fire. So everybody will throw some butt in there, and that's a problem. And these butts are getting too frequent and killing the goose.
Steel, if they can do it, why not? You put the insulation.
Yeah, but you see how passionate steel people are. We know that. So they will rise to any challenge. So I'll leave it at that. Right?
Sir, we have one question from my answer.
Oh, there's okay. I didn't even realize that. Yeah.
So what is the difference between the mixed design from normal configured use fibers in it?
Yes.
Do we require high strength material?
Yeah, we had a whole Gyan course that delved in a lot of depth in that matter. At this point of time, I'm not able to give that fine detail. There are enough papers on that. And at this point of time, we've come to a stage where we can develop these mixes in a scientific manner. We cannot follow the same mix procedures as what are laid in 10262, which is our base guide for concrete mix design. That will not work. But procedures are evolving, which basically looking at the aggregate, the cement content, etc. Now we can develop 3D printable mixes. The one exception is that the mix that works in one printer may not work in another printer, because the pressure states are going to be different. The entire process by which it's extruded is going to be different. So for each printer, we'll have to develop a mix that will work for that specific printer. And yes, we do use fibers now. We use a smaller percentage of the microfibers for shrinkage, as was brought up before. But now we are talking about, in fact, this is where I think we're all headed now, is to take it to a much higher volume fraction of very fine steel fibers, almost to the extent of making a UHPC out of it. And then the sky is my limit, because now I have these thin filaments which have tremendous tensile capacity, tremendous material ductility, and I should be able to directly print with it. So I can then deliver actual structures without having to worry about reinforcement. And so I think that people are already working on it.
That's a natural progression.
Natural progression. There's a group in China that already claims to have printed with UHPC. And we, in our lab also, we now have just last week, we were able to pump UHPC. We're starting to print with it as well. So the idea is that the whole bridge I could have printed with UHPC. I'd be able to save much more on the material. And I think net we'll have a winner there, is my opinion. Right? So then these become structural walls, like you're saying. And I don't need to resort to putting this conventional reinforcement and all that in there. Right? So. Yes.
Interactive very big as actually, compared to conventional concrete, in a conventional we will aggregate interlocking.
Correct.
Can I able to use aggregate interlocking in between the layers so that
That's what that stitching was all about, remember? So this, if you remember, I said that there are two reasons why, what I'm worried with stress transfer is between the layers is my primary concern. So there was this, there's this group in Japan, what they have is a robot that comes along and simply goes around inserting nails which go between the layers, and what that's doing is stitching the layers together. So it's almost like a sewing machine that's going behind the filament and sewing the two layers together. So that's also being worked on. Right?
Whenever you are doing this research, how are you collaborating with this pump manufacturer? It appears to be very interdisciplinary.
It is. So this is not something that you can basically sit in one domain and get it to work. Otherwise, you're at the mercy of all of these different vendors. We are fortunate because we have a very large center in additive manufacturing at IIT Hyderabad, which is in the mechanical engineering department. So we are able to leverage their strengths. So I don't have to worry about technology when it comes to basic things like the robotic arm control and all these things. Pumps, yes, we are working with pump manufacturers in India. Otherwise, we were beholden to pump suppliers like Putzmeister, who are basically the largest suppliers of pumps in the world. But then ultimately they own the technology, they hold us hostage. So now we are working with local pump manufacturers to get the proper pumps that will allow us to deliver on the capacity. But yes, it's totally interdisciplinary. Unless you have a team that's able to draw upon from different fields, it's going to be very difficult to do research in this.
Sir, with weak interfaces, how will you do a pre-stressing in beams?
Okay. Suppose I stack multiple layers, right? And so you have all these layers. So let's look at it this way. These layers are like stacked up like this, right? If I pull on the layers, each layer will come out very easily. Instead, if I compress it, what will happen?
It will have high strength.
So basically now, I'm taking advantage of the pre-stressing. So it's like putting a rubber band around it, right? So I basically compress it. Now to separate the layers takes a lot of force, isn't it?
Actually, you pre-stress it vertically.
Yeah, so we pre-stress it across the layers.
Okay, sir.
Okay, so I create a printed, like the example of the bridge I showed you, right? So I created this box section where basically if you look across the box section, it is made up of multiple layers. Then I insert a pre-stress layer here, pre-stressing here, and pull the pre-stress. What happens? Each of these layers goes into compression.
Okay.
Right?
It's a regular segmental precision.
So basically,
Now the shapes are different. They can optimize.
and each shape can be different. So each segment can have a different shape, and I can print it for you. Right? So there I'm basically relying on the pre-stressing and the exact same principle as what you have in this thing, where basically I keep use pre-stressing to provide that pre-compression, right? And now it takes a lot more effort to separate these layers, right? And in doing so, I'm able to give you a structural system which can resist loads. Okay? Now, whether it will behave the same as regular cast construction, then the answer is no. It will still have that anisotropic behavior because of the interfaces. Whereas in cast construction, it is one monolith, one piece of concrete. That you have to contend with, right?
When speaking in LCA, why didn't you go with geopolymer?
Sorry?
When speaking in LCA, why didn't you go with...
We have. This is just an example of concrete. We have printed geopolymer structures as well.
Okay.
Now it will open up to wonderful shell structures.
Absolutely. Yeah. In fact, I'm not showing it here, but we are
Compression members.
actually printing it, airport hangars for defense. So we have optimized this eggshell shaped structure, and you basically for where these aircraft can come and stand, and printing with UHPC. So I get this thin shell where I take advantage of the shell structure because it's very strong in plane.
we are printing in contact and the fiber orientation will be along the direction.
Yes, you do get a preferential fiber orientation effect. So the design approach would have to be different. So you basically, that's why we are, if in a structure like this, we are taking the lattice approach. Right? In lattice, what do? You basically treat it as if it's a 1D element, right? What happens in a truss? How is it different from a beam? In a truss, you have 1D elements, right? The stress transfer is taken up by 1D elements. What happens in a beam? You get a two-dimensional stress field, even if you take a plane strain or plane stress idealization, it's a two-dimensional stress field. So what have we done in this example here is we've taken the continuous stress field, replaced it with a lattice. So then all it is about this single lattice element, whether how much tension or how much compression it can take. So that the fundamental design approach changes then. Okay?
Sir, can we use two robotic arms to reduce the time?
Yes, you can. In fact, we're working on this synchronous printing with two robotic arms, where this is something that we're working on, where you have the outer shell being printed, and the outer shell doesn't need that precise geometry control, where we'll print it using larger aggregate, 10 mm aggregate at this time, where there's inner lattice, this fellow, I can basically make it finer, make it a variable thickness, but then I need much higher resolution. So you have two robots that are going around doing the printing. And so yes, it can be done.